Hello and welcome to Lecture 3 of Charge Separation and Storage in PHYS 1204. We're going to keep looking at capacitors but get more quantitative as we look at the quantity that characterizes a capacitor, which is what we call its capacitance. We're mostly going to restrict our attention to parallel plate capacitors, which are the type we've been looking at the most so far. And that's because everything we really need to know about capacitors we can learn from parallel plate capacitors, and they teach us a lot of other things about electrical interactions. But capacitors come in all shapes and sizes. They can be cylindrical and all sorts of other geometries. And if you look in any piece of electronics, you're going to find a lot of capacitors. In this picture that I just randomly pulled off the web, all of these things I've circled are things that I recognize as capacitors. Many of the other things in the picture may be capacitors as well, I just don't recognize them as capacitors. However, while an engineer may care about capacitors mostly because they're all over the place in electronics, a physicist cares about them because they're all over the place in nature. Because a capacitor is any pair of oppositely charged conductors. So, a cloud and the ground below it are a capacitor. And the cell has a membrane around it, and the solutions on either side are conducting, and so the cell membrane is a capacitor. There are many ways, using only things we already know, to show that for any capacitor, the charge on the plates must be proportional to the potential difference between the plates. Here's one way of seeing that that must be true. Think of a path, starting on the negative plate and ending on the positive plate, and think of carrying some probe charge QP along that path. Then we know that by definition, the potential difference between the plates is the negative of the electrostatic work done on that probe charge divided by the amount of charge it has. And we know that that work is proportional to the E field strength, because the E field is what is producing the forces on the probe charge, and those electric forces must be proportional to the amount of charge on the plates, because those are the charges that are exerting those forces. And so we see that the potential difference must be proportional to the charge on the plates. Well, that means we can write an equation that says the charge on the plates is just some proportionality constant times the potential difference between the plates. And that proportionality constant is what we call the capacitance of the capacitor. It's a property of the particular capacitor, and for that capacitor, once we've measured it, we know it's always the same. And it's determined by geometry, the shape of the plates or the conductors that the capacitor is made of, how far they are from each other, how they're oriented with respect to each other, and so on. And it's also determined by what the material is between the plates, which is what we've seen as the dielectric. Let's look at units. So, as usual, charge will be measured in coulombs. Note a source of possible confusion here, because charge is in coulombs, C, the quantity capacitance is being represented with a C. Okay, so we'll be careful. So, coulombs here is equaling capacitance, which I'll make a C inside a square to keep it separate, times a potential difference, which must be in volts. And so that tells us that a capacitance must be measured in coulombs per volt. And that is defined as the farad, capital F for farads, which is named after the 19th century physicist Michael Faraday, who did a lot of the very early work developing electromagnetic theory. Note that just like the coulomb, we know the coulomb is a very big unit, the farad is a very big unit. If you take a 1 volt battery and attach it to a capacitor, you don't expect to get a 1 coulomb charge on the plates. That's huge. Although you can, in fact, go out and just buy a 1 farad capacitor. But most capacitors you come across in electronics have capacitances in the nanofarads or even picofarads. Microfarads and millifarads are also fairly common. What we now want to know how to do is calculate the capacitance for absolutely any capacitor. And there's a procedure that will work for a capacitor no matter what shape its plates are and no matter how they're oriented relative to each other. First, just assume that the conductors are carrying some opposite charges of magnitude q. And I do mean q, not any specific number, just q. It's all going to cancel out in the end anyway. And you now find the E field along some path from the negative conductor to the positive one. You can find that E field any way you want. Superposition of fields, Gauss's law, whatever's easiest. And the reason we need to know the E field along a path is that we're going to find the electrostatic work on a probe charge that moves along that path. Remember, these plates are conductors. And so the potential is the same everywhere inside one of the plates. So it doesn't matter what point we choose on the negative plate and what point we choose on the positive plate. The electrostatic work done on the probe charge going from one to the other has to be the same along any path. These are path independent after all. And so you could choose a hard path. There are any number of hard paths for any conductor that you can choose, but you might as well choose the easiest path possible and calculate the electrostatic work along that. And then you know that from that electrostatic work you can get the potential difference between the plates. Now all you have to do is take the charge, divide by the potential difference, and that gives you the capacitance. And note that all these charges will have cancelled, because we know that the potential difference has to be independent of the probe charge used, and we know that the potential difference is proportional to Q. And so the Q, which is the charge on the plates, will have to cancel out as well. And so what we end up with is a quantity that depends only on the geometry of the plates and what's between them. Let's now use our general procedure for finding the capacitance of a capacitor to find what the capacitance is for a parallel plate capacitor. So step one, remember, was that we assume that there is a charge plus Q on one plate and negative Q on the other. Okay, well that's an easy step there. Done. Now we need to find the E field along some path inside the capacitor. Well, for the parallel plate capacitor, that's also very easy because we found that long ago. We know that the magnitude of the E field inside the parallel plate capacitor is the charge density divided by epsilon naught, and we know that that E field everywhere points straight from the positive plate to the negative plate. And so we know its direction and we know its magnitude everywhere. The next step is that we choose a path, the path that we know the E field along, but that's easy because we know the E field basically anywhere inside this capacitor. And we need a path that leads from the negative plate to the positive plate. Our nice, easy path is going to be one that is parallel to the field. And so it just runs from a point on the negative plate straight across parallel to the field to a corresponding point on the positive plate. And so that is just a straight line of length s. I'm going to define some axes. I'm going to set my origin on the negative plate with the x-axis pointing from the negative plate to the positive plate. Now we need to find this electrostatic work. So we know by definition that it is going to be the integral of the electric force dotted with an element along the path, integrated along the path. Well, that's simple here because the electric force on our probe charge is parallel to E. And so that force is just the probe charge times the E field. And along our path, which remember is going from the negative plate to the positive one, the angle is 180 degrees. And so we know that Fe dot dr is just Fe, which we know is QPE, dr cos of the angle between them, which is 180 degrees, and so that's just -1. And so there is our electrostatic work. We have a constant probe charge and E field that we'll just pull out in front of the integral. All the vectors are gone. We are integrating with respect to x from 0 to s. And so that's a very easy integral. Now we use that to get our potential difference between the plates. We know that that is just the negative of the electrostatic work divided by the probe charge. And so we can see that that's just the negative takes out the negative, the probe charge takes out the probe charge, and we're just left with ES, which we've actually seen in an earlier unit. And so finally, we can simply say that the capacitance is the charge on the plates divided by the potential difference. And so that is the charge over ES, but I know that E is sigma over epsilon naught. And sigma is Q over A. And so the charges on the plates cancel, and all we're left with is that the capacitance is going to be epsilon naught A over S. And there is the capacitance of a parallel plate capacitor. Let's use this to estimate a fairly typical capacitance. So a fairly typical capacitor looks like this. It's perhaps about the size of the end of your pinky finger. And remember that although it's a cylinder, it's actually a parallel plate capacitor. It's just that the plates are rolled up into a cylinder. And pretty typically, those plates would be about 1 centimeter wide and maybe 10 or 20 centimeters long, and would be separated by the thickness of the dielectric, which is basically a thin paper impregnated with some sort of oil in many cases. So that's enough information for us to at least estimate the capacitance, although we're going to be assuming that it's just vacuum or air in between the plates. Actually, the dielectric has a large effect, but we don't know how to calculate that yet. So let's estimate that. We know that this is epsilon naught times some width of the plate times some length of the plate over the plate separation. And what I've said is that width is around about 1 centimeter, and that length is around about 10 centimeters, pretty typically. And the plate separation is similar to the thickness of a fairly thin piece of paper, let's say 1/10 of a millimeter. That's actually pretty thick. And if you just plug that into a calculator, you'll find that it comes to around 8.85 times 10 to the negative 11. And let's just check units. All the meters are gone, and we get Coulomb squared per Newton meter. That is Coulomb squared per joule, or coulombs per joule times coulombs. And a joule per coulomb is a volt. So that's coulombs per volt, which is what we knew it had to be. That's farads. And so this estimate has come out to be around about 90 picofarads. Note, the side of this capacitor tells you that it's about 330 microfarads. This is a pretty big capacitor compared to what we've just calculated. That'll be due to several factors. Almost certainly the plate separation would be smaller than this. That's important. The plates may be a little bigger than this, but far more importantly, it'll have a dielectric in it, and that makes a much larger difference.